Everyone, Mr. Neighbor here, and we're still talking about motion and forces. So, when we talk about forces, we tend to illustrate those with something called a free body diagram or FBD. So, a free body diagram is a diagram showing all the forces acting on an object, the force's directions with its magnitude. So, here's an example of a rock climber propelling down a cliff. So here you just see the rock climber. Here you see the free body diagram for the rock climber and the different parts. So when we look at free body diagrams, we always make one for an object. And then for a different object, then we make another one. So for example, this actually has two free body diagrams in it. The first one is the one with the man's center of mass. So right here, the pull of the rope in blue and pull of gravity. Then we have a second one with the friction of the cliff and push off the cliff. So this is like the foot's free body diagram, and then we have the man's free body diagram. Typically, when we're working in this class, we only have one free body diagram for a single object. It's not a complex one like this. But let's just think about all the forces acting on the man. We have a rope pulling the man up. That's a force due to tension. Typically, we label that with F and then sub T, or you could even write out tension in little letters. Then we always have this force due to gravity that's pulling the man down. We write F and then a little G there to show that. The friction of the cliff. So the rock climber is propelling down. So he is pushing off the cliff. So that's why that arrow is right there. So we could say that is F applied. I tend to do F and then an APP for that, because air resistance will do F air. So we don't want to confuse the letter A with applied or air. So that's why I write out APP. And then the friction of the cliff. Friction always goes opposite motion. So if the motion is down, then the friction is going to be up. So we'll label it F, and then I tend to do a lowercase f for friction. So we're going to do a few examples of free body diagrams. So here's one where we have a cart being pulled. What does that say? A free body diagram of the cart being pulled by the back, pulled by the boy and held by the girl. So that's supposed to be boy. That's why it's confusing. All right, so this big dot is going to represent our object. So there's my free body diagram. It's a pull by the girl, or sorry, a pull by the boy. So that's a force, I would say tension, because there's a rope involved, and it's being pushed by the girl. That girl is pushing it in the same direction as the boy is pulling it. So I'm going to draw another arrow, and that's going to be the force applied. Now, I like to add my arrows on top of each other, so then I can see that the net force is those things combined. So the net force is this long blue arrow. So I know that is going to accelerate in the rightward direction. All right. Create a free body diagram of the water skier being pulled behind the boat. Oops, I forgot one thing. Sorry about that. Up on this one, we forgot to label two very, very important forces. There's always a force due to gravity, unless you're in outer space and not near an object. And there's also a normal force. There's a force from the ground pushing up on the cart so it doesn't move in the Y direction. So these two forces are equal in magnitude, so they cancel each other out, but they're opposite in direction. So technically, this normal force, it would be applied to the wheels, but since we're doing one free body diagram, we do it in the center of the object its center of mass, and we kind of just combine the little normal force right here. So normal, when I say normal, it means the word perpendicular. And in math, perpendicular means right angle. So it's a force from the earth that's at a right angle to it. So perpendicular. So if an object is ever touching a surface, there is a normal force. It's the surface force. It's the holding it up force that counteracts gravity. So back to our water skier. Sorry about that. So that's this guy. We're not talking about the boat. They have forces acting on them, but I'm only talking about the water skier. So first, you have the force of gravity. Next, since it's not accelerating, you have the normal force. Should be the exact same magnitude, opposite direction. Then you have a force pulling the guy along. I would probably say that's a force due to tension. And you probably have a little bit of friction from the waves. So a little friction force. So for this example, it looks like when we add up our vectors, they're not going to be as long as the tension force, but there will still be a net force to the right. Because our one force will go this far, and our other force will go this far, and then the leftover chunk is the blue to get from the starting point to where we ended right there. All right. Create a free body diagram of the basketball flying through the air. So the basketball, it has the force due to gravity. It's not touching a surface, so there is no normal force pointing up. The person actually threw the ball, so there was an applied force, but that was then. That's not now. Now there is no applied force. It's just going on its path that it was set on. We could talk about air resistance if we wanted to, but in this case, since it doesn't have a very big surface area, we're going to neglect air resistance. You could put it on if that's the peak, the highest it's going to be, the air resistance would be going back this way. Not that we need to get into that right now, but I just wanted to point out that you could write it. You wouldn't be wrong if you did write it, but force of gravity is really the only one we're looking for. So then the net force is just the force of gravity. Now, the net force is not part of the free body diagram. This right here is the free body diagram. The net force I just like to put on there. Oh, is that all of them? Okay, well, there are a few examples about free body diagrams, so hopefully you can do those now.